Hey, so we're going to start section 3.2, and 3.2 is all about graphing functions. So we'll start with an example of graphing the function f of x equals 2 over x. And a graph of this function is just like the graph of a curve, where we'll draw our xy axis, except now we keep the x-axis labeled x, but we no longer have a y in the equation, we have an f of x. So instead of a y-axis, we have an f of x axis. And then to figure out what the graph looks like, we're just going to plot some points. And so we start with a table of points to test. We'll mark x, and then have the corresponding output f of x. And we'll test the values 1, 2, 3, 1/2, 1/5. And we'll know that f of 1 equals, let's write that actually as f of 1. F of 1 equals 2 over, where we see an x, we now put in a 1. F of 1 is 2. F of 2 is 2 over, where we see an x, we put a 2. 2. That equals 1. And I'll let you work out the details for 3 and 1/2. And you should find that you get 2/3 and 4. And for f of 1/5, we get 2 over the fraction 1 over 5. And when you're dividing by a fraction, you just flip the fraction and multiply. So that's going to be 10. So our graph looks something like this, where at small numbers we're big. Just clean that up really quick. That should be a 4. Then at 2, we're over at 1. And as we increase, we don't decrease that much. So for positive x values, our graph looks something like this. So then a question is, what about negative x values? Well, if we plug in a negative value, we should just get the negative out, right? If we have f of -1, we get 2 over -1. That gives us -2. And so because the graph has this, what we called symmetry about the origin in prior videos, we know that on the negative side, it's just going to look exactly the same, just reflected across this line. So that's the graph of our function. Graphs can be a great way to visually represent data or to understand the function. So when you're looking at, if you're looking at just the equation, f of x equals 2 over x, maybe it's a little hard to pick out what values of x are going to be small or what values are going to be large, which ones are going to be negative. When we have the graph, we can see that if x is negative, that implies f of x is negative. Big values of x, gives us small values for f of x. And that's really all there is to it, to graphing. In the following sections, we're going to work out more connections between properties of functions and how that translates to them being on the graph. So we'll talk about how to identify when a function is positive by looking at the graph, how to identify when a function is increasing in value or decreasing in value just by looking at the graph. The takeaway from this is that we'll just be plotting points to graph our functions and connecting those. This works well for pre-calc, but it doesn't always work well for all functions in particular. And I'll give an extreme example. There's this one crazy function. It's called the salt and pepper function, where it's 1 if it's rational, is not rational. And so remember, rational just means that the number can be represented as a function, as a fraction. It's like 2, 1/2, 1/4, 7/10 are rational, but the square root of 2, the square root of 3, pi are not rational. So the graph of this function looks something like, it's hard to draw. It looks something like this, where these aren't actually two overlapping lines. Like, it's still going to pass the vertical line test, but the problem is that as close as you want to any rational number, there's an irrational number, and as close as you get to any irrational number, there's a rational number nearby. So if you tested only rational numbers, which is what we usually do, then we would always get f of x equals 1. And if we didn't test any irrational numbers, then we'd never have a place where the function is 0. So we'd miss out on the whole bottom line. So that's an extreme case, but usually this method of interpolation, that's where we test points on the function and just try to connect it in a logical manner, does work pretty well. In a particular example, we usually, corporations will usually use their quarterly profits and create an interpolation to think about how their company is changing. So they might have a graph that looks like this. So maybe you have 2018's quarter 1 profits. So over here would be 2019's quarter 1 profits, so on and so forth. The big idea is that they basically just have different levels of profits each quarter. And so maybe they're at values like this, where maybe they're selling a seasonal object. So sometimes they make more money, sometimes they make less. We would use an interpolation to kind of connect these dots. So something like this. to understand how they're changing over time. So we can see that it looks like the function is increasing in value and there is variation from each quarter to quarter. So here it's, these two are low, but these two are high. And the idea is that this interpolation works well because we wouldn't expect the company to have any sharp spikes. So maybe a place that would have a sharp spike is, say, in the middle of this quarter. We could gain a lot of money, then lose a lot. So we could have had, so maybe in reality, it had some giant spike like that. But we didn't know about it because we didn't have this data point. But when it comes to companies, we tend to think that this is pretty rare. So the interpolation of just connecting the dots works. All right, that's it for 3.2. We're going to talk more about graphing functions, properties of functions in the subsequent sections.